Hello everyone. Today I'm going to talk a little bit about line, surface, and volume integrals in preparation for the ASEN 3111 Exam 1. That's aerodynamics. This is a part of the calculus review that we've been putting out with the Aerospace Engineering Fellows. My name's Connor. Let's get into it. So, line integrals, right? So when we're talking about line integrals, and right here we're talking about it in context of a vector field V, wrong color, vector field V, and curve C, right? So when we have a line integral, essentially what we're saying is how much of this quantity V accumulates in the direction and over the distance, over the length of curve C, right? So essentially what we're looking for, and I've drawn a very nice vector field that lines up with our curve pretty well. So if this curve goes from 0 to end, 0 to end, essentially what we're looking for is we add up all the pieces of this vector field that are in agreement with this curve, right? So at every point, and we'll break this down, we'll look at the one little point, we'll say at every point, we have some portion of it, and we'll say this is length ds, and in direction ds, right? This is just some part of the curve, right? And you also have some component of field, we'll say we're evaluating at this point, and it's not quite in the same direction as ds, right? But there is some component of it, right? And whenever we want the component that two vectors share, right, we take the dot product, right? So we take the dot product between these two, we're gonna get, so this is v dot ds, that gives us what these two share, and we can integrate all the way over that from 0 to end, and I'll have a more in-depth example. This is kind of just the gist of it, but we're basically adding up everything that agrees, right? And you can take this a step further. We can look at this in terms of a closed integral where C loops all the way around. It connects with itself, right? And usually if you're trying to figure out, is this a closed thing or not, try to imagine, think to yourself, does this have an inside and an outside, or a left or a right, So an inside and an outside means, it's closed, right? If it's a left or a right, there's maybe two sides of it, but there's not really, there's an opening. You know what I'm saying? So I would stick with the inside or out thing. The left or right thing doesn't make a lot of sense now that I'm saying that out loud, but same kind of deal. We can add up all the little pieces that are in agreement, and actually for us, because these are in opposite directions, we can see that we're going to have a bit of a negative agreement here, right? If we took the dot product between these, we get up something like this. This is negative compared to ds, so that would detract from the sum as we go all the way around, and then it would accumulate more as we're down here because the vector is more in line. The vector field is more in line with the integral or with the curve, and then it would kind of sum to 0. There's not really, it's kind of perpendicular, and then we add up, and then we start subtracting more again over here, right? Very exact same thing as we do over here, though. We integrate from 0 to the end. Now we can take this a step further, and we can say, don't look at that other picture yet, it's not ready. We can look at surface integrals, right? So we can what we're saying here is basically how much of this field agrees with the normal of this surface, right? Surface is not necessarily all in the same plane, but essentially what it is we're looking at how much of this goes in the same direction of out of the plane or out of the surface, right? So if we draw our little ds right here, right, our ds light, we'll draw a little normal vector out of it, and we've got some vector field going out here. It's the same thing. This is our normal direction, and this differential area, you can call it d capital S, you can call it dA. I usually stick with dA, it makes a little more sense to me. But we add up, we take, however much these two align times the area that ds takes up. So we end up with something that's like, here, let's draw this, we'll see. Well, the integral over the area, right? And we'll do a double integral because there's two dimensions here of v dot n ds. And usually capital S. No, I said I was an A person. I'll stick with being A. I'll stick to my guns. Usually what we do is we write these as like, one quantity, so we'll call it the integral over A of V dA, right? We add up everything that these two share with each other, and we'll multiply it by the area over this, we'll add up over the area of this surface. Just like those, let's look at this bean here, right? We can also have a closed surface integral, right? And remember how I was saying, if it's got an inside and an outside, it's closed, right? This is the very same thing, except usually, we always define n to be outside of the shape. So if it has an inside, then n goes outside, right? And it's the same concept. We're adding up everything that these vector fields share with each other, or share with the normal to the surface. We add it up over the area of the surface. Right, volume integrals. There was no cut there. Volume integrals. So essentially what we're doing here, so now we're adding up, and I'll draw a little extra sum in there. We'll draw a little dV, a little box of volume. Right? That's not the V I'm looking for. Right? And what we're doing here, right? Imagine we have this little window into our volume, and we're seeing the scalar field inside through our window. What we can do is, essentially what we're doing is we're adding up all of the scalar inside this volume, right? So we for every little piece of volume, let's keep the colors right, am I right? For every little piece of volume, right? There's some mass in there. How about we say that, right? We'll say we'll stick with density, right? So if we multiply this density over this volume, we get this little differential mass element, right? And if we want to add all those up, and we'll give ourselves a little more space, we'll add all those up with a triple integral over the volume, and we'll get the total mass inside this volume, right? And you can do a similar thing with vector fields integrated over a volume. The definition is less, the physical meaning is less apparent, but you can do the same thing. You can integrate over the volume of V dV. It's totally a valid integral, right? And you're still integrating, the vector field kind of taking up space in these volume elements, right? So that's all I have for these volume integrals. I'll have another video that's just a quick example of doing a line integral, something you might see on an exam. So look for that. And thanks for watching. Have a good night.